how we use machine learning to fill our logistics engine. Uh, but maybe before starting, you probably already know know Wolt. Some of you might have ordered from us, like you might know us from like delivering food to your door. And I was briefly introduced before, like one thing that I need to insist here, like we don't only deliver food, but we also like deliver all type of items that you can think of. Like in case of retail, for example, like we can do like from clothes or to flour, alcohol in some cities. We have like a wide variety of things that we deliver, and we have also a quick commerce branch, World Market. And I'm telling this because it obviously affects how we do logistics, because we have a lot of different logistics use cases and a lot of different deliveries use cases. So you don't need the same time to deliver like 10 pizzas, and just wrapping a couple of bananas in a bag and getting them delivered. So like these are definitely an impact. So overall, our aim is to get whole city delivered within minutes. So we are with our target. We grow in that direction, and this like really take care of like all different delivery line in this case. Speaking about Volt, as was introduced before, like it was founded in Helsinki in 2014, and then we expanded massively in Europe, East Europe, and like went to the east. We are like Japan is probably the furthest located market that we are in compared to Helsinki. Yeah, to so 27 countries, 500 cities. That give you some idea of the scale and the type of operation that we work in, because obviously deliveries depends really on the cities and on city landscape. We have like over 10,000 people in the team globally enabling this operation. We are over 800 people in the product team, like building the platform that enable this operation. 36 million registered user, like 140,000 merchants. Like give you some ideas there, and something also to note, like usually one of the a really well rated app on the market in the market we operate in. And speaking about logistics platform, so basically what I'm meaning here is like we are building a platform which connects three entities, like customer, couriers, and merchants. So we have a courier app, a customer app, and a merchant app. And our aim is to get to connect them so that customer can get items or orders delivered from any given merchants by courier partners. And again, like why I'm giving these introductions is because when we speak about logistics at Wolt, in logistics we are at the center of this. Like logistics is we are connecting these three parties, and we have like a direct impact on how these three parties perceive Wolt. Like we can have like a positive impact on customers, like providing them like makes a customer experience a delight and making sure that we can increase the loyalty. We can also facilitate merchants operation, like predicting the right pickup time, like when the courier will be at their venue, to make sure that like in busy time we provide them the right amount of information so that they can get the order as smoothly as possible delivered. And for courier partners, we want to provide them optimal tasks. We want to make optimal use of their time too. So this gives you some context about like where we stand in logistics. The question now is like, where does machine learning take place here? And if you think about it as a so maybe before going to on machine learning, they give you some overview like where logistics or the logistics pipeline. So what you see as a customer too is like you have this you first arrive on the app, you can select a venue, browse to the venue, select to an order, place an order. You get some update about your delivery. At some point, your order is there. So quite simple, but what takes place in the background while you are doing this? And this is basically our logistics pipeline. Like what takes place, all the steps that takes place between you ordering and the order arriving at your door. So once you place an order, we first need to contact merchants and ask, like, can you fulfill this order? Can you prepare it? How much time do you need to prepare it? And when they confirm the order, then we need to prepare the merchants start preparing the order. In parallel, we need to find the right courier partners to deliver it. So we optimize the allocation of the courier partners and select the fulfillment and select which courier partner should take it, offer him the task, and then they start fulfilling the pickup. So that means that they travel to the merchants, arrive at the merchants, pick up pick up the order, might be some delay, and then like goes a drop off and then go to the customer and drop off the delivery, like so. Between the moment you place the order and you receive it, all these steps take place, and this is what we want to optimize. So here, like how we see machine learning there, like the most simple use case that you can think of as a customer when you see like this flow, we provide you delivery ETAs before you order. And this is some like probably the most simple use case you could think of. Like you want to know like when your order will arrive, and we use machine learning models to predict this. So maybe why do these estimates matter? And I think it's pretty clear to everyone that if we provide like really too low delivery estimates, you'll have lateness. What it means in practice is like quality of service costs. A customer will contact support, and you have like a real human being answering your request, supporting you to understand like where your order is, when you will arrive, and so on. So it has some cost to be like predicting really high ETAs. But on the other side is what people usually oversee is the earliness cost. So if we provide like too high delivery estimates, the customer wants the order to arrive as soon as possible. And in this case, like we miss opportunity to satisfy a customer. We cannot really, they won't order because they think it will arrive too late, although we could have delivered it much earlier. So when we think about this pre-estimate, this pre-checkout delivery estimates, we always play with this trade-off about we want to be as accurate as possible to avoid both earliness and lateness. Next step is like why predicting this is really so complex. What makes pre-estimates prediction so complex? And in fact, I already told you that in the introduction, is the scale at which we operate. So like you saw the delivery timeline, like preparation is part of it. You don't prepare the, take different time to prepare the order, being like if it's a food delivery or like a retail or like a quick commerce. So like this has a major impact. Similarly, we have like 140,000 merchants on board. Every merchant will have his own preparation time, his own process, and we need to take that into account when predict the estimates. Like 230,000 courier partners, like we have like a lot of diversity and like in different vehicle types that they might be using in different cities. And the scale also at how many users you want to provide these estimates to. So we want to have like low latency at scale. And similarly, like if you think about, we operate in 27 countries, 500 cities, like every country is different and they will have a different landscape. So think about traffic, try to imagine like traffic in Stockholm compared to Tokyo. Like it's fully different. Or like traffic to Stockholm and Espoo in Finland, which is like much smaller. Or like weather data. Like I guess snow in Stockholm like might slow down the traffic, but you'll be still like I guess the full city wouldn't be blocked. If you go to Athens, I guess like snow might have like a different impact. So we really need to take that into account when we predict our estimates. And so I gave you some context, maybe like now, like how do we predict this pre-estimates, so pre-checkout delivery times. So yeah, I guess a classic, we just take a simple ML model and feed data into it. Like it's what what we all do. One thing is like we take a simple model. Like it's really important to mention. Like we predict one model to predict end to end. We don't like try to predict like okay how much preparation time will be, pickup times, and drop off time. Like not at the pre-checkout phase, but instead we use this type of information in the features that we use. Like we try to account for this in the features. For example, like we look into what the delivery distance as type of features, like what the delivery distance is between the venue and customer, because that will have an impact on how much, how long courier partners need to travel to deliver it. We take into account venue-specific information. For example, like how much time the venue needed to predict to prepare the order in the past, and we can look at historical data for past weeks, past days, past 30 minutes, like really different type of time aggregates to be able to take that into account. And obviously city states specific features. So classic is like how does supply and demand looks like? Do we have like many orders at the moment and few couriers? Or like what's the ratio between ongoing deliveries and active courier partners? Because that will have direct impact on delivery time. We also like look at average delivery and preparation time in the past 30 minutes at the city level, like how busy is the city at the moment. Think like how fast can we send courier partners to the venue currently, and weather. Like as I mentioned before, like weather is definitely some impact factors that can affect delivery time. So these are the type of features that we consider when building a model. On the model side, quite simple, keeping things simple, tree-based model, so XGBoost, I think it's standard. I doubt I need to introduce that one. We have a lot of categorical data, so we are mostly using target encoding. Not sure if you're familiar with that. It's basically you take you link one category data to some aggregates of your targets, so you can see like as an aggregate, you could feel like average delivery time and like what's the average delivery time for retail. And in your like every time it's a retail order, you say like that's the average delivery time and encode that with that. So the target encoding to feed that in XGBoost and like yeah RMSE laws. So quite yeah, we kept things simple. Why we chose this, and I think it's quite standard. Like there was a new paper about it. Like everyone knows that tree-based model is better for structured data. So like a common knowledge, I guess. But the question is actually, is it the case? So if you look at this data, so we're doing some benchmark about like tree-based model versus deep learning, and if you look in details, like the title is really like catchy, but if you look in detail, like the benchmarks that they did, they consider like really small data sets, like 50,000 samples in the data. They limited the cardinality of the categorical data like to 20, like it's really small. And now you compare it to our scale. Like we have 140,000 venues. This could be like cardinality of a categorical data. You compare it to 20. Does it hold? Like, or the number of samples compared to our registered users, like it's really much a different scale. So this is why also we are currently working on the next generation model, and yeah, using deep learning, obviously like exchanging the XGBoost for PyTorch, using embeddings instead of target encodings. Like we can better handle our large cardinality and train more complex, learn more complex representation. And yeah, also playing around with some losses too, and like still working with it. So this is what when I meant next generation model. Also yeah, and also we are using PyTorch Lightning actually for as a library there. So when I meant about yeah next generation model, we actually like A/B tested already a simple model there, and we so by default we A/B test everything that we do. And we already like, even with the simple models developed in some weeks, we already increased accuracy by over 6% relative. So it's massive, quite a massive improvement for like such small in compared to the development times that we needed, and we can really like so it opens us a lot of opportunity. So we are now working to deploy that really at scale. So maybe I can give also some a bit more like deeper insights there. Like I mean, what I wanted also to mention on like some of the learnings that we did here is like more about the technology that we use. We're using PyTorch Lightning. Why we chose this one of the main reasons was that we can organize our code much better, which at our scale is quite important. And we have integration with MLflow and a couple of useful things like metrics. It's easy to define metrics, to use custom one and existing one, early stopping in deep learning, quite standard. And there's like also the opportunity to they have some. It includes some heuristics to define which learning rate you should be using for your model architecture. So it's a really sweet feature that is enabling us to iterate really fast. Speaking about iteration, basically it's how we do things. Like we build quick models, and we iterate a lot. Try to ship really regular iterations there, and it's really how we need to deploy machine learning. For that, we need a solid MLOps stack, obviously. So we are using mostly open source software, Flight for model retraining and training on clusters easily. MLflow for model tracking, I guess no need to introduce it. And Seldon Core for deploying model at scale. So now I gave you some overview of like how we do like one of the simplest use case and like how we model it, like the use case that you see as a customer basically. The question is what is behind like when we do logistics? How can we improve our full logistics pipeline by using machine learning too? And here comes another use case about using machine learning is like so-called fulfillment estimates. So basically we are using machine learning model to predict how much time courier partners will require to spend to execute a given task, because we need to have this to fuel our task allocation engine. So why this fulfillment estimates matter? It's simple. Like you can imagine, we agreed on the pickup time with a merchant. So the merchant say at that time, at 6 p.m., I will get the pizza will be ready. You can pick it up. And then we need to estimate how much time the courier partners requires to arrive at the venue. If our estimation is correct, perfect. Like the courier partners arrive, the pizza just got ready, you take it and go directly to the to the customer. Like no waiting time, it's just perfect. On the other side, if we underestimate the pickup time, like how much time the courier partners requires, the courier partners, the order will be ready, but there is no courier. The courier is still on the way. So the pizza is waiting. You have like food waiting time. The pizza get cold, but you have also like longer delivery time. If a courier partners had been there earlier, then it could already be on the way to the customer, and we would have been able to deliver in much shorter time. But on the other side, if we were to overestimate the pickup time, then it means that we send courier partners too early on task. They arrive early and they wait at the venue. And then you have like courier waiting time and longer time spent on task. So it's not also like, it's a suboptimal utilization of the courier partner's time. And we always have this trade-off with fulfillment estimates about logistics efficiency, like how much time courier partners spend on task, and average delivery time, like how fast can we deliver to the customer. And this fulfillment estimate, like depending if we overestimate or underestimate, we have a risk of going into one of the direction. That's why we also need to we need to have like really accurate delivery time, fulfillment estimates. In practice, how do we model them? So we have like two type of fulfillment. Like we have two cases. Like you have the pickup fulfillment and the drop-off fulfillment. So like how much time the courier partners requires to pick up the food, and how much time does he need to drop off the food. And both of them, we decompose them in two steps. So we have like travel time, which is like how much time the courier partners requires to arrive in the neighborhood of the target, like to the merchant, like how much time does it require to come close to the merchant or to the customer in case of drop-off. And then the service time is like how much time does it require to take the last 10 meters or like 100 meters. So like once he's in the neighborhood, like how much time is spending like to find the venue. So we have this these two targets, like we decompose them in this way, and how they are used. So in our task allocation algorithm, basically, at each time step, we look at the set of deliveries that we need to perform, like pick up and drop off, and we have information about online courier partners, like with location and currently ongoing tasks. So that's the only thing, and vehicle types. That's what we consider. And we enrich this information with machine learning models in order to create like service time for like a given type of courier partners. Type, I mean like vehicle type in this case, and and travel time for a given vehicle type. And then we feed all this information directly into our task allocation engine, like a vehicle routing problem solver. So we use directly these estimates in our task allocation to optimize a vehicle, to solve a vehicle routing problem. And we get out of it an ordered list of tasks that we want to propose to courier partners and the corresponding estimated ETAs. So like this fulfillment estimates have a direct impact on task allocation too. So now I introduce a use case, why we have them, like how we decompose them, like I explain a bit, like give a few words about how we actually compute them. So we have travel time. How do we compute travel time for courier partners? Uh, Actually, if keeping things quite simple, we use map services like external, so either like self-hosted OSRM maps or like OSM-based with OpenStreetMap-based services, or like in some of the markets we have like map providers. But we are operating in like really large scale with many different countries. So we always try to find the optimal map or map provider per country, because maybe like the coverage of one map provider wouldn't be the same in Stockholm or in Kazakhstan. So like they have different, you might have local actors which are better. So we are looking to this, but we have also like OSRM based one to use that for many of our markets. And where does machine learning takes place here is if you look at actually the prediction of the OSRM base, like when you look at by vehicle types, OSRM by default have some speed assumption about speed for a given vehicle type. But we actually find out that on our use case, like the speed of the courier partners provided by predicted by OSRM doesn't necessarily match like the actual speed of courier partners for a given vehicle type. And we can actually correct them by using simple multiplier correction. So to account for the speed difference, like in different cities, for example. So what we do in practice, we train machine learning model to compute this correction that we need to apply for a given fleet, a given vehicle type, and a given hour for everywhere we operate. And yeah, we train simple machine learning models there. The idea is like we take anonymized segments of former deliveries, and we look at how much time OSRM predicts like we will need to use, and how much time the courier partners actually needed, and use that to train a model and apply that on our data. And the other use case that we have like service time, and I could really explain why it matters, but basically a few words about service time. Like it's so service time basically it takes the time that it takes for courier partners to find the venue or the customer to reach them once they are in a given neighborhood. So for example, like why we produce that, because like depending on the area, we might have a different service time. Like finding a parking spot, for example, might be different in city center than outside of the city center in residential area. Or like if the venue is in a shopping mall, then you might need a bit more walking distance to go there, or like taking elevator for like a customer in a given building. So we use machine learning to predict this and to take that into account in our planning. In practice here, like we have two models, two separate model for pickup and drop-off service time. And yeah, at the moment we're still keeping things simple, like gradient boosting. We'll probably scale to deep learning in one upcoming iteration. The type of features that we're considering here is like average service time, obviously for a given venue, but also like in a given neighborhood, like looking at neighborhood for customer or venue. The order size, like if the courier partners is transporting a large bag, you probably need more time to walk than a small bag. And vehicle type, like you don't need the same time like in as a bike or a car driver in a city center compared to suburban area. And yeah, and for MLOps, similar usual suspects on on our side, like flights, Seldon Core, and MLflow. So like we definitely deploy these models at scale too. So we need to have like a solid MLOps pipeline there. So I gave some overview now, like on how do you compute these fulfillment estimates. I like to close the loop on like how like what you see as a customer, basically like the order tracking. Basically, once you ordered, you see this screen like tells you like, okay, your order will be in 15 minutes, and where does it come from? And similar side on the merchant side is like how we do like how do they get this like pickup estimates, and here like also like quite simple use case, and we actually mostly use the actual plan and look at this travel time and service time planning that we have, and compute the delivery ETAs out of them, like directly out of it. So yeah, like overall, like maybe a quick recap, and like what I show you today is like mostly about like what you see usually as a customer. Like the first use case that you can think of is like really pre-estimated, pre-delivery estimates, and the complexities that we have behind it, due mostly actually to the market we operate in, like the diversity of the data that we have, more than the actual algorithm that we use. I think this diversity is one of the main challenge that we are facing in general in logistics, and this is something like really needed to highlight. And we have fulfillment estimates, like how these fulfillment estimates also affect logistics and like our the performance of logistic engine, like computing travel time, service time, and yeah, and finally closing the loop on the order tracking DVTA. So that was about the use case. Maybe like as a closing remark, like I'm on stage today to present this use case, but data science is a team sport, and it's definitely like I'm definitely not the only one behind it. I wanted to give some word about like the people I'm working with. So the way we operate at Wolt is like we work in fully autonomous team, like we fully own a domain, and data scientists are fully embedded in the team, which enable us to get things deployed really easily and to have like really always get the engineering bandwidth to deploy things. In my case, I'm data scientist engineering, so we work directly with engineering to build tangible things. But we have also like designers, data scientists, analytics will enable us to perform a lot of analysis, experiments, and product leads, obviously. So these are like people behind me, and I obviously like at World we're like as many companies we have a lot of core values. I think I just wanted to have this slide because yeah, so I believe that many people actually all people in my team embodies this core values. So like this why we managed to iterate fast. We have like really a lot of excellent people and long lot of heart and like will to learn and teach. So it's really nice. And yeah, but I wanted also to mention, like, we are also scaling our Stockholm tech hub. So if anyone is interested, we have like open jobs. Feel free to check or reach out at the end. So that's it on my side. Thank you for listening. I hope you enjoy the talk and like presenting the use case. If you have any questions, happy to take them. Just great.
Do you want a mic?
All right. Just a question on the use case where you're predicting time to drop off.
Yep.
So if I am as a customer, so my question is, do you personalize the predictions based on customer? So for example, if I'm a customer, I remove the name on my front door and the courier gets lost every time and it ends up taking maybe like 15 minutes more. Would you be able to pick that up eventually if I would remove it tomorrow? Will you kind of personalize the predictions based on collected data about each individual customer?
At the moment, no, and it's not like we do that mostly by neighborhood, like by for a given neighborhood. But we are working on improving things. So this is something that we try to take into account. But like usually it's mostly anonymized data, and it also depends on like past predictions. So past every time too, obviously.
Okay, cool, thanks.
Hey, thanks. Great talk. Out of curiosity, like in the breakdown you had with the collect and drop off times, what is the value of the ML part here? Like if you would just do brute force vehicle routing plus, I don't know, use a mean for the wait time or something like that, what is the improvement in accuracy by adding an ML layer on top of it?
I couldn't comment on the exact improvement in accuracy, but in practice we observe like massive improvement. We found that it has a massive improvement in our use case. Also mainly because it also the ML layers help also to take into account the diversity too, because like eventually you could have like a simple number, but that simple number would need to account for like vehicle type, like how much time do you need to travel it, like to look at location, or like the type of events, or the type of the size of the order, because you have like different travel time. So eventually you would need to have like separate different values for that. So in this case, you will be ending up building a large heuristics, would be like where a machine learning model would be able to better generalize across different use cases. Does that answer your question?
Not really, but but I understand your answer. So yeah, thanks.
Yeah, I wouldn't be able to comment on like on the value of the accuracy, because I think when we introduced you, it was also before I joined, like on the exact side. But like on each iteration, we notice like a noticeable business impact eventually.
Yeah, great talk. Thank you. I'm interested in digging into the kind of the costs of being too early and too late. Do you treat those equally, or could you quantify like, you know, an unhappy customer service call is actually more expensive than you know, somebody waiting a bit longer to pick up an order?
So we are working on quantifying it definitely, but it's not always easy to quantify both. So like we try to quantify to find the right balance, but it's also like overall we try to have like the most accurate model in. So we mostly track accuracy usually, rather than on the other.
Thank you.
Sorry. Just follow up. So how do you measure accuracy in this?
So it's a really excellent question. Like we usually, I mean, by accuracy I mean like for example like plus minus x minutes. Like our model is mostly like based on single point estimates that we apply some range on top of that, and we look at plus minus X minutes, basically around the range. So that's how we measure it in practice. For example, like if we predict 20 minutes, like will it arrive within plus minus 20, between like 15 and 25 minutes.
So there's like, is there some, does that tie into like why you're using squared loss for, or is that just because it's easy in XGBoost?
Yeah, I mean, square loss is like, obviously, like it's kind of like a skew. We have a kind of a skewed distribution because we cannot have negative delivery time, unfortunately. So it's skewed, and like square loss also partly enable us to capture like longer tail in this case. But it's this is also why what we work on, like working with different laws, trying to find what's the best use case in our case to maximize accuracy in practice.
Cool.
Hey, great presentation, thanks. I just was wondering, in one of the slides after this one, you mentioned that after you predict the delivery time and feed an algorithm with all the available courier, that the algorithm pick which courier to assign the tasks, is that correct?
Yeah.
Yeah, this one, exactly. Yeah, this one. The allocation of the task is also performed by machine learning model, or is that pure algorithmic?
Pure heuristic.
Is there a reason why like that? Or do you think a machine learning model could perform better?
It's an excellent question. I don't think, I think like heuristic will probably work better than machine learning model. So I don't, I'm not best placed to answer that one because I'm not working partly on that one. But until now, I haven't seen any machine learning algorithm which was was outperforming this heuristic basically for many use case, because we have also a lot of constraints, obviously, like depending on delivery types and different like timeline and so on. So I think like machine learning model might not be, and you need to train it on something too, if you're wondering.
Yeah, exactly.
So yeah, I think in academics there's a couple of machine learning models to do that, but in like reinforcement learning based model, we read a couple of articles about this, but we didn't believe it would work in our scale of operation.
Thanks.
Yeah.
And I also have a question for the drop-off time. I was thinking from the restaurant to the home of the customer, you basically also calling the API from the, let's say, Google Map, and they will give you quite specific time to delivery. And what's the actual value to use machine learning, since they also have real-time data? They know that route have traffic jam at this time. So why are you trying to predict?
It's an excellent question. There are many use cases, like as I mentioned, like we are working in many different countries. So Google Map accuracy might not be as accurate in all different countries that we operate in. So that's one of the reasons. Scale too, like Google Map might not be able to provide like, I mean, think about it here, like for example, we need to provide for each possible courier partners, each possible pickup and drop-off tasks, we need to provide routes. If you need to call Google Maps every time, then you'll be spending most of the time actually waiting for a Google Maps answer. So I don't think they can provide like matrices durations there too. So like this type of consideration, and costs probably too.
Good to know. Thanks for answer.
I have a question, if that's okay.
Yeah.
So back in uni, I used to do a lot of queuing theory and, Poisson processes, for example. It's a typical telecom, use cases.
Yeah.
Have you ever looked at something similar to that? Maybe like a Bayesian approach where you have some priors on estimation time and things like that?
We consider that. I remember like we discussed that at some point for one of the use case difficulties that also our scale, like for most of the Bayesian approach, might be a bit difficult, like the number of data samples that Bayesian approach, at least from what I know and my experience, is like really at smaller scales are perfect, but like when you start to have like a really large scale and a really large number of samples, and it might be a bit more tricky.
Nice, thanks.
I have a question regarding the models that you use for this specific use case. Do you use any advanced or big deep learning models that could benefit from using PyTorch Lightning for the training?
I mean, like PyTorch Lightning in our case, like I think it's independently on the type of the model. Like PyTorch Lightning is providing us the right structure basically to standardize how we train deep learning model. Like that's what I was meaning before. Like first step, why we use that is also like organizing code. Like once we start using deep learning for more of the more use case in PyTorch Lightning, you don't need to rewrite your training loop. That's what you will do in PyTorch. Like it's coming out of the box. You have like mostly callbacks, and it has a lot of nice features. Like for example, like learning rate tuner. When you start playing with a lot of different architecture, you always need to adapt them to a batch size and so on. Here's like it comes out of the box. That was mainly the reason.
Okay.